Hello, this is Dave Enyart. This is the Hyperledger Fabric Sprint 2 demo for the Ledger component. We've been working on Fab 60 for the last 2 weeks. This is an initial prototype of plugging in various databases for the state database underneath the Hyperledger Fabric. And there's a chart deck attached to the Jira work item, and I'll show a few slides from that chart deck to get oriented here. Okay, so in version 1, the blockchain ledger itself is comprised of two different data stores. The first is the actual blockchain. That's the immutable source of truth, and that is written to the file system. And then there is a state database, which is, you can think of it as an index into the blockchain, and this is for optimized runtime queries. Similar to prior versions, the state database writes the latest values of each document or variable within chain code, and so it's there for transaction execution. And in version 1, there's the separation of the endorsers and the committers, peers, and so the state database is used for simulation of transactions. There's also a proposal to store the actual transaction documents within the state database so that they become queryable as well. In this case, you can query the past transactions and the history of various assets. So the focus for the pluggability, or one of the focuses for the pluggability, is on the ability to query the blockchain. So in the key value database, such as RocksDB, which has been used in prior releases, the variable is actually just a blob, and it's opaque, so you cannot query anything within that blob. But if we use a document database such as Couchdb, we are now able to store the value in a way that we can query it, and especially if we model it as JSON, we are able to query the data within the chain code variable. So this can meet auditing and simple reporting requirements, and also allows for some query from the chain code itself. With this approach, it's also possible to plug in other data stores. For example, you could plug in SQL data stores. And to review the transaction lifecycle for version 1, I mentioned there is the endorsing peer where simulation takes place, and I've highlighted here where the plugin would get invoked. So during simulation, the plugin would get invoked to query the state database for any simulations of transactions. But when we actually write or do a put state within the chain code, those are not written to the database, but they are saved in the read-write set of the transaction that gets sent to the ordering service. From there, the ordering service sends the batches of transactions to the committing peer, and this is where the values actually get committed to the blockchain and the state database. And before we do that, we actually do a validation check first, which we call the MVCC check, to make sure that the variables have not been changed since simulation. So during the MVCC check and during the commit, the plugin is used to write the values to the state database. Okay, so I'm going to demonstrate the pluggable and queryable database using a Couchdb database. This is the JSON document store, and I'll be using the marbles example. I can pretty much use the marbles chain code as is. This chain code uses JSON already, so it's a good fit with really no changes in terms of how the APIs are called. And I've got a plugin for Couchdb, and when we commit and actually write the transaction, we'll be persisting to Couchdb itself. So the scenario is we create a marble. It's initially owned by Tom, and then the marble is transferred to Jerry in a subsequent transaction. And then we'll be able to query the document and the transactions using various Couchdb query examples that you see here. Let's switch over to the code, and you can see All the green files here are the new files related to the Couchdb plugin. We have the Couchdb transaction management package, and we have an example for the Marble client application and the Marble chain code. And we also had a few updates to the Queryable to create the Couchdb transaction manager as opposed to the lock-based RocksDB transaction manager. So we'll be looking into some of the main files, including the Marble application, the Marble chain code, and then some of the underlying code. Okay, so let's take a look at some of the code here. We've got, for demonstration purposes, a Marble app that acts as the chain code. And this chain code has the create marble and transfer marble methods. The create marble will take in a list of attributes for the marble and then create that using a simulator set state. Okay, and then the transfer marble will take attributes including the marble name and the new owner. It will get the marble from the state database, in this case Couchdb. It comes back as JSON. It's actually a byte array representing the JSON. And then we unmarshal that into the marble structure so that we can set the new owner and then marshal that back as JSON and then use the simulator to set the state again. And you can see throughout I've got debug statements with Couchdb here. This will make it easy to see in the log that we'll take a look at next. Okay, so in front of this pseudo chain code, we have a client application that calls into that. It calls into create marble and transfer marble, and this is the piece that choreographs everything. So it will call the simulation to get a transaction. It will then act as the consenter or the ordering service to construct a block from this transaction. And then it also has the mock committer to commit the block. Okay, so when we run this, we'll get a handle to a KV ledger, and this is where our switch is to use Couchdb instead of RocksDB. So there's a flag here that you have to set in the code for now, where we can set use Couchdb to true, and if so, then it creates a Couchdb transaction manager, passing in the connection information, so the host, the port, the database name, and the ID and password, which I have as blanks here because I have a Couchdb that does not have security set up yet. Okay, so when something like the commit actually gets called at the end of the day, this will write any transaction read-write sets into the state database and also the blockchain. And so to actually this is the commit on the transaction manager or the state database itself. So what we do here is we save the document. In this case, the document is the actual JSON document. And that is represented here as the value. K is the key of the document, which will become the document ID in Couchdb, and the couch connection information. From here, we've got a wrapper around Couchdb to actually do the HTTP put to save the document. Finally, let us run the example. So we'll run the marble example, and this will again create the marble and transfer the marble. And we can see all the logging here with the Couchdb statements. Let me go up to the beginning. Okay, so here is the create marble, and I won't go through all the details, but you can see that it's the create marble gets simulated and then validated and then committed. And here you can see the JSON that was I actually sent down to Couchdb. So it's sent down as marble1 owned by Tom. And then we call the transfer marble. And if you look at all this trace again, you can see that it is simulating this and then validating and then committing it. And when it ultimately gets committed, it gets created, updated. The marble1 gets updated as owner Jerry. Okay, so now it's in Couchdb, and we can go verify that. We can look at the documents in this database, and we see here that we've got marble1. We can take a look at some queries then, and I'll do that using the REST client. So Couchdb has a REST API to query documents, and let me first query for the marble document here. Okay, so it found the marble document, and here you can see the owner is Jerry. It says here there's no matching indexes, so I have not created indexes yet to make these queries faster. So once we do that, we'll get very quick responses for these queries. Also want to show the transaction history query. So right now I'm not writing transaction documents yet, but I have a couple there mocked up so that we can see what this looks like. But if we were to query the actual transactions, and in fact we're querying the read-write set within the transaction, looking for the asset name of marble1, and we would get back two transaction documents, one for the initial create and then one for the later update. Okay, so this has been the Sprint 2 demonstration for Ledger, and we'll talk to you next time. Thank you.